All right. Hello, everyone. I'm Sorrachai, Yingchareonthawornchai. So I will be here in the whole semester, and then after this, I will start a postdoc position at Hebrew University. Today, I will tell you about the recent progress in Vertex connectivity. And before that, I want to introduce a bit about my own research interests. So other than Vertex connectivity, I'm interested in combinatorial optimization problem, generally on graph connectivity, network design, or flow problems. And also, I'm very much interested in data structure problems. And I'm in particular on the connection between amortized analysis and the extremal combinatorics. And my favorite problem is dynamic continuity conjecture, which involves something about the performance of splay trees and geometry of the magnetic search tree and so on. And I'm very much like to work on this kind of date conjecture or traversal conjecture. So we have some like recent progress along this line. So if you're interested, I can also share more about this progress. And now, so let's continue. So let me first define the vertex connectivity problem more formally. So I give you a graph, undirected graph with n node and m edges. So we want to compute the minimum number of vertices such that when I remove from the graph, I disconnect the graph. And for example, in this graph, the connectivity is 2 because I can remove these 2 nodes to disconnect the graph, but I cannot delete a single node to disconnect the graph. And next, I'm gonna, before I state all the survey of the result, I want to also mention the list of collaborators in this area. So Danupon Natongkai, Tachapon Sanurak, Sebastian Foster, Jason Lee, Debmaya Panikaki, Chaitanya Naram, and Yong Kang Jiang. So at least three of them are present in this program. Okay, let me give you a quick survey of the vertex connectivity problem. So the complexity, it was like first studied in like 1969 by Kiteman, and the complexity is about mnk squared. So now k, you can think about k as like the optimal cut, the size of the optimal separator. And on the third column is just when the graph is sparse, this is the simplified complexity is quadratic. And what do we know in the literature? So in a very classic work, they can also improve the running time to be something of this form, n plus k squared. And with the randomization, Baker et al. Managed to improve the complexity to be mn times k. And a bunch of so there are some recent progress, some progress using a specific edge specification by Namaguchi Ibaraki that you can specify the edges to be only order nk. And also you can use there's also the reduction to matrix multiplication. So you can solve the technology using matrix multiplication. And this was the state of the art due to High-Single-Rao and Gable that give the randomized algorithm that solve vertex connectivity in m times n. And here is like the complete picture before I start this problem. So the next one is Gable gave the deterministic algorithm that is quite almost mn but not quite mn. But the challenge in this area when I started was that if you look at the special case when the graph is sparse, then the complexity has been quadratic. So the first goal, if anything, is that we need to break this quadratic barrier, right, to make progress to this problem. Yeah, and also at least Hopcroft and Ullman also asked whether or not there's a linear time vertex connectivity algorithm in this area. So it asked like almost 50 years ago.
This is all undirected.
This bar was for event directed. Yeah, yes, event directed. I want to emphasize that, look at this state, the runtime still mn, even if we assume linear time max flow. So we still need something more to make progress on this. And so the first result that like we show that for small connectivity, we managed to break the quadratic barrier. In fact, we can get up to like almost nearly linear time. I wanted just to mention that the key new ingredient that make this progress possible is like the paradigm of the local computation and probability testing that was like introduced in this area. And then this allow us to give the improvement. And just to say something, just to say a few words about local computation. So I gave you a fixed node S, and then the question is that is there a small unbalanced cut that contains S? And then I want to be able to detect this cut like in sublinear time. So I don't want to read the whole graph, but I still want to be able to decide this. So this is the kind of question that enable us to make progress in the small vertex connectivity. What I also want to highlight a bit that like the algorithm is so simple that it's also implementable, and then we also show some experimental result that is actually scalable. It's also you can run in real world graphs. And here so for small connectivity, we know how to do it near linear time. But the next question is how about larger connectivity? What do we know about that? Can we do anything better than MN? So for this question, so let me rephrase the literature in the context of MaxFlow computation. So basically, let me introduce this subroutine called ST vertex min cut. So this is also similar to the variant that Jason mentioned in the Edge version. So I give you two nodes S and T. I want to compute the minimum vertices that separate S and T. Right? So and then this problem can be also solved by MaxFlow in MaxFlow time. And then given this subroutine, you can also solve vertex connectivity trivially by just running all pair MaxFlow, and then you just find the minimum so far. So this is a trivial algorithm. You can do n square MaxFlow, and there are some progress on reducing number call of MaxFlow. So this is to rephrase the previous literature in the context of MaxFlow. And then the best reduction was n times call of MaxFlow due to Baker et al. And and then for the small connectivity, we know how to do like almost linear time, but for higher connectivity, the previous algorithm cannot scale for high connectivity. So what the recent progress is that like we also managed to get something of the form that vertex connectivity can be solved in polylogarithmic of MaxFlow, but the algorithm is randomized. And the key tools that we introduced into this area involve the kernelization, some sketching and sparse recovery, and also the use of isolating cut lemma from the Edge version. We also adapt it to the Vertex version. And because of the recent breakthrough in MaxFlow, so now we can also say that, okay, Vertex connectivity can be solved in almost linear time. And this answer open problem by Hopcroft and Ullman. Now that's great. Vertex connectivity now can be solved in polylogarithmic MaxFlow, and what else? What are the questions left? So what about the deterministic algorithm? So I will give you a quick survey on the deterministic version of because the previous polylogarithmic MaxFlow algorithm is randomized. So what do we know about deterministic algorithm? So I just one key motivation to study is that in the sibling problem of edge connectivity, so they are like much much more well studied than much well understood compared to vertex connectivity. For example, in edge connectivity, as like Jason gave a survey already, that like we know how to do randomized very long ago by Carter, and then later on, there's also a way to like do de-randomize totally in 14, and then also very recently we can even know how to de-randomize on the weighted graph. But for vertex connectivity, the context, the picture is different because so this is the state of the vertex connectivity. This is randomized, but the best deterministic algorithm is by Gable. So give the running time of something like n to the 1.5 MaxFlow. MaxFlow. So you can do n to the 1.5 MaxFlow, or you can do k square MaxFlow by like since like even 25. And the state of the art of vertex deterministic is that like m times n is also an open question whether or not can you get the deterministic vertex connectivity in m times n. And only linear time algorithms are known for very small connectivity, like the constant connectivity. And then there are some recent progress on this deterministic regime. So let me elaborate a bit. So the recent progress is that like last year, we know how to do it like in almost linear time for very, very small connectivity. Let's say C is like, K is like square root, little o square root log n. So we know how to do this. And then there are some very recent progress that we know how to do in K square MaxFlow, and also do n MaxFlow And I want to emphasize that Nmax flow here is like still fresh. It's still happening during the workshop here. So it's still something coming up, very exciting progress is coming up. And I want to add a few keywords of this technique that we developed along this line. That we, for the first one, we developed something called vertex pacifier, and we use the vertex expander to make this work for small connectivity. And then we do some usage of the terminal reduction and accelerating cut lemma for the k-square max flow. And then the last one, like N max flow, is to do the randomization of the technique in the kernelization from the previous one. And I want to conclude with some exciting open problem that I feel like it's also still, we're still quite far from it. That can you do deterministic algorithm for the connectivity like in near linear time? Can you do this? And we know how to do that for constant complexity, but it seems like super difficult to get something better than MN. So whether or not can you also find some separate lower bound from this, that would be very, very interesting. And I also want to mention that directed is also open. Like if you look at the directed connectivity, then the running time is either mc square or n square. Both are randomized. And then if you look at weighted connectivity, it's also quite far that the running time of weighted connectivity is m times n. So either like making progress on this area or like establish some conditional lower bound, this would be very, very interesting. So that I would like to conclude.
Any questions? Yes.
Yeah, if I may, a stupid question. Can you go back one slide? So for the edge connectivity, the last two, let's see, result of big O tilde of m and m to the 1 plus O of 1. I mean, I'm a bit confused about what is better between the two.
So this one is slightly slower than this one, but this one works for even weighted on the weighted graph. This one is unweighted.
Oh, so this is the main difference.
Yeah. So this is like stronger in the sense that it works for weighted graph.
So you said that this uses expander decomposition. Is the type of directed expander decomposition you would like for this problem related to the one that Jason talked about?
It is like undirected, but it's an expansion in the sense of the vertex expansion, not the S expansion. So it's slightly different, but it's similar.
But this could be one of the ingredients that you would need to get the directed.
I think that's also one possibility that like if you can generalize this notion vertex pacifier and the vertex expander to directed version, then you will get the directed version. Yes, but there's some barrier on the generalizing vertex pacifier to directed setting. So yeah, it's also quite challenging.
But is the definition of these things clear? What it should be?
Yes, it's well-defined object.
Yeah. I wanted to see in the last slide, well, the reference for so weighted vertex connectivity.
Yeah, by yeah, it's by Yingchareonthawornchai and Gable.
Yeah, it's funny it hasn't gotten. So these modern techniques have not.
Yeah. So it seems like the technique that we have, like for the unweighted, doesn't seem to be usable for the weighted setting. So it's very interesting because in the edge connectivity, when you have the weighted graph, it's very easy to generalize a sampling method to the edge setting. But when you have vertex, then the same trick does not work somehow. Yeah. So it's very interesting if there's some technique that can handle the weighted graph.
Okay, well, let's say again.